Hello everyone. Today we will study about hydrogen bond. Let's consider some examples. Let's consider a hydrogen fluoride molecule and also two different bonds, an HO bond and an HN bond. Now in this HF molecule, we know that fluorine is more electronegative than hydrogen. Therefore, the shared pair of electrons or the covalent bonded electrons will be shifted more towards fluorine so that fluorine will get a negative charge and hydrogen will get a positive charge. In the case of HO bond also, since oxygen is more electronegative, oxygen will get a negative charge, hydrogen will get a positive charge. Similar is the case of HN bond also. Now we know in these examples, this fluorine, oxygen and nitrogen are electronegative so that the atom bonded to these atoms, that is in this case hydrogen atoms, will be electropositive. So this will result in a polar molecule in the case of HF bond and polar bonds in the case of HO and HN bond. So this results in the formation of dipoles. Now consider another HN molecule, HN bond, which comes closer to this HN bond. Now in this bond also, nitrogen is negatively charged, hydrogen is positively charged. Now if these two molecules come closer to each other, this nitrogen, that is a negatively charged nitrogen, will be attracted to this positively charged hydrogen of the second HN bond. So there is an electrostatic force of attraction between the negatively charged nitrogen of one HN bond and positively charged hydrogen of the second HN bond. Now this type of bond is what we call as a hydrogen bond. Please note that hydrogen bond is an electrostatic force of attraction between two atoms. Electrostatic means attraction between opposite charges. Now, if another HO bond comes closer to this first HO bond, this kind of hydrogen bonding will also occur there because this negatively charged oxygen of the first HO bond will be attracted to the positively charged hydrogen of the second HO bond. So in this case also a hydrogen bond will be formed. Similar is the case of HF molecule also. Fluorine, negatively charged fluorine of the first molecule will be attracted to the positively charged hydrogen of the second hydrogen molecule. So in this way, if another HF molecule comes here, there will be again electrostatic force of attraction between this negatively charged fluorine and the positively charged hydrogen of this third hydrogen fluoride molecule. So in this way, a number of hydrogen fluoride molecule can associate together, resulting in the formation of a large cluster of molecules. A long chain will be formed like this. So let's try to define hydrogen bond now. Hydrogen bond is an electrostatic force of attraction between a covalently bound hydrogen atom and a small but a highly electronegative atom, like which are their examples, fluorine, oxygen and nitrogen of the same or another molecule. Now in this particular example, the hydrogen bond is formed between two different molecules. This is one HN bond in one particular molecule. This is another HN bond in another molecule. If you take this example of hydrogen fluoride, this is one HF molecule, this is another HF molecule, and the hydrogen bond is formed between the fluorine atom of the first molecule and the hydrogen of the second molecule. So in this case, the hydrogen bond is formed between two different atoms. But hydrogen bond can also be formed within a molecule. We will see examples of such hydrogen bonds later. So hydrogen bond can be formed between different molecules or with same molecule, one atom, a hydrogen atom and another electronegative atom of the same molecule. We will see such examples later. So this is how we define hydrogen bond. It is electrostatic interaction between a covalently bonded hydrogen that is a hydrogen which is already bonded to another atom, and a small but more electronegative atom of the same or another molecule. And the atoms which can form hydrogen bonds, examples are fluorine, oxygen and nitrogen. Now let's study about the nature and strength of a hydrogen bond. As we have already discussed, a hydrogen bond arises due to the electrostatic force of attraction between this positively charged hydrogen atom and a negatively charged atom. In this example, the electrostatic force of attraction exists between the positively charged hydrogen atom and the negatively charged fluorine atom. So since a hydrogen bond just involves an electrostatic force of attraction, it is inherently a weak bond, unlike a chemical bond. We cannot say that hydrogen bond is a chemical bond. Hydrogen bond is not a chemical bond because it does not involve any kind of sharing of electrons or donation of electrons. So hydrogen bond is not a chemical bond. Please understand, this is a very important point. Hydrogen bond is not a chemical bond. It is just a force of attraction between two opposite charges. That is, it is just an electrostatic force of attraction. And since it is not a chemical bond, a hydrogen bond is a weak bond. So if you compare the strength of a hydrogen bond and a covalent bond, it is obvious that hydrogen bond is much weaker than covalent bond. If you check the strength of these bonds, hydrogen bond or the strength of a hydrogen bond is only between or in the range of 10 to 40 kilojoules per mole, whereas a covalent bond will be almost 10 times more stronger than a hydrogen bond. Its strength will be around 400 kilojoules per mole. So you can see a hydrogen bond is much weaker than a covalent bond. Now let's compare the electronegativity of fluorine, oxygen and nitrogen. As we have studied in the earlier semesters, fluorine is much more electronegative than oxygen and nitrogen. Because of this, the strength of hydrogen bond in an HF molecule will be much greater than the strength of hydrogen bond which exists between hydrogen and oxygen and also hydrogen and nitrogen. Because since fluorine is more electronegative, it will be more strongly attracting this bonded pair towards itself, so that fluorine will be much more negative and hydrogen will be much more positive. So the force of attraction between this negatively charged fluorine atom and this positively charged hydrogen atom will be much more when compared to the bond between hydrogen and oxygen and also hydrogen and nitrogen. If you compare the strength of hydrogen bonds between these two, we can see since oxygen is more electronegative than nitrogen, the strength of hydrogen bond will be much greater in this particular case than in the case of H and L. Now let's see what are the conditions for hydrogen bonding. Means for a hydrogen bond to be formed between two atoms, two conditions has to be satisfied. The first thing is that the atom bonded to hydrogen should have high electronegativity. Say in the case of a HF molecule, as we have seen, fluorine is very electronegative than hydrogen. So that is why it can form hydrogen bond. So the atom bonded to hydrogen should have high electronegativity. The second condition is that the atom bonded to hydrogen should be very small in size. Why should it be very small in size? Because if the atom bonded to hydrogen is very small, it can attract the bonding electron pair effectively. Now, all atoms cannot form hydrogen bonds. The most electronegative atoms, fluorine, oxygen and nitrogen, are the atoms which can form hydrogen bonds. Because in these molecules, the conditions are satisfied. That is, these atoms have high electronegativity. They are very small in size. Also, they can possess lone pair of electrons which can interact with hydrogen atom in hydrogen bonding. So the atoms which form hydrogen bonds are nitrogen, oxygen and fluorine. Now let's see the different types of hydrogen bonds. There are two types of hydrogen bonds. The first one is intermolecular hydrogen bonds and the second one is intramolecular hydrogen bond. Intermolecular hydrogen bond occurs between molecules, whereas intramolecular hydrogen bond is formed within the molecule. Okay, inside the molecule itself a hydrogen bond will be formed. Let's see first what is intermolecular hydrogen bond. As we have mentioned, intermolecular hydrogen bonding is formed between two molecules of same or different compounds. This is one example, hydrogen fluoride. As we have seen, hydrogen fluoride can show or can form hydrogen bonds, and one HF molecule can form hydrogen bond with another HF molecule, and then in this way a number of HF molecules can associate together to form a long chain like this. And this has been already proved. It has found that in solid state HF exist as a long zigzag chains of molecules, and these chains are formed because of hydrogen bonds. Means these molecules are associated through hydrogen bonds. So in solid state it is not correct to write the molecular formula of hydrogen fluoride as simply HF. It should be written as HFN times. Why? Because in solid state, HF exists as long zigzag chains of molecules. A number of molecules are associated together as a long chain. So it should be written as, the molecular formula should be written as HFN times. Now on heating we know a solid will be converted to a liquid at its melting point. On heating what happens here is, the bond between, the hydrogen bond between this H and F, since it is a weak bond, it's only a neutrostatic force, we have already seen that. So because of that, this hydrogen bond will be broken, or this electrostatic force of attraction between hydrogen and fluorine will be broken. So it will split into a number of HF atoms. This association will be broken. So the hydrogen bonds break, and what happens to the chain length? The chain length will shorten and it becomes linear. In the solid state it was in a zigzag manner, but as we heat it and it forms a liquid, or if it is converted to a gaseous state, it becomes linear. So in the liquid and gaseous state, the molecular formula of hydrogen fluoride should be written as HF itself, but in the case of solid state, its molecular formula should be written as HFN times. Now consider this fluorine atom. How many hydrogen bonds will it form? If we consider this particular fluorine atom, how many hydrogen bonds will it form with other hydrogen fluoride molecules? So if this is a fluorine molecule, as you can see, it will form only one hydrogen bond with another HF molecule. This is the hydrogen bond which is formed with other HF molecule. So fluorine atom in a hydrogen fluoride forms one hydrogen bond with another HF bond. Now consider one HF molecule in this state. This is the hydrogen fluoride. Consider this HF molecule or HF bond in this chain. How many hydrogen bonds will this HF molecule form in this chain? This HF molecule forms two hydrogen bonds. One is this bond, the second one is this bond. Right? So an HF molecule forms hydrogen bonds with two other molecules. Now okay. So please bear in mind, in this HF long chain, fluorine atom forms one hydrogen bond with another HF molecule, and each HF molecule will form hydrogen bonds with two other molecules. Now this kind of association is not present in other halogen acids. Means we have considered hydrogen fluoride. If you consider other halogens, halogen acids, that is hydrogen chloride, hydrogen bromide, hydrogen iodide, etc., you cannot see this kind of association. Why? Because chlorine, bromine, iodine, etc. cannot form hydrogen bonds. We have already seen the conditions where an atom can form a hydrogen bond. The first condition is that the atom bonded to hydrogen should be more electronegative and also it should be small in size. These two conditions are not satisfied by chlorine, bromine, iodine, etc. Therefore, hydrogen bonds are not present in HCl, HBr, etc. It is present only in hydrogen fluoride. Now this is another question which can be asked. KHF2 is a molecule which actually exists. It has been proved that KHF2 is a molecule exists. Now how is this KHF2 formed? It is formed between the hydrogen, formed by hydrogen bonding between a KF molecule and an HF molecule. So it can be written as KHF2. But molecules like KHCl2, KHBr2, etc. do not exist. As we know, fluorine, chlorine, bromine, all these are halogens, but only KHF2 exists. KHCl2, KHBr2, etc. or such molecules do not exist. Why? Because as we have already mentioned, chlorine, bromine, etc. will not be able to form hydrogen bonds. Therefore, a bond formation like this is not possible. That is, a hydrogen bond formation between KCl and HCl is not possible. Therefore, KHCl2 molecule and KHBr2 molecule do not exist. Only KHF2 exists because a hydrogen bond can be formed between fluorine and hydrogen. Now another example which forms intermolecular hydrogen bonding or which shows intermolecular hydrogen bonding is water. Now this is the extensive hydrogen bonding shown in water. Consider this water molecule. This is one water molecule. You can see many other water molecules like that, and this water molecule is forming hydrogen bonds with other water molecules. So in this way, hydrogen bonding in water is very extensive. Now please check. Consider this oxygen atom. How many hydrogen bonds will it form? If you consider this oxygen atom, you can see it forms two hydrogen bonds. The first bond is this is the second hydrogen bond. Dotted lines represent hydrogen bonds. So oxygen atom forms two hydrogen bonds with hydrogen atoms of neighboring molecules. Now again consider this oxygen atom. You can see it is surrounded by hydrogen atoms. How many hydrogen atoms are there surrounding this oxygen? 1, 2, 3, 4. So you can see each oxygen atom in this cage-like structure is tetrahedrally surrounded by 4 other hydrogen atoms. Okay, consider this water molecule. How many hydrogen bonds does it form with other molecules? This water molecule forms 1, 2, 3, 4. 4 hydrogen bonds with other water molecules. So these are important. You should study this. So in this way, you can see a water molecule can form a 3-dimensional network by associating with other water molecules. It forms a cage-like structure of water. So actually it is not correct to write H2O water. The formula of water is H2O. It should be written as H2O n times because it forms extensive hydrogen bonds. Ammonia is another example which shows hydrogen bonding. As you can see, there is one negatively charged nitrogen atom and 3 positively charged hydrogen atoms, and the hydrogen bonding is shown like this. Now, the second type of hydrogen bond is intramolecular hydrogen bonding. Intra means within the molecule. So this kind of hydrogen bond is formed between hydrogen atom and an electronegative atom of the same molecule. And this kind of hydrogen bonding is called chelation. I can say this intramolecular hydrogen bonding is commonly called as chelation, and it is more commonly found in organic compounds. It is not found much in inorganic compounds. It is mostly found in organic compounds. Also, this intramolecular hydrogen bonding results in cyclization because it is formed between hydrogen atom and the electronegative atom of the same molecule. So the molecule will cyclize itself, or it results in the cyclization of molecules. And if this happens, it will prevent association with other molecules because a hydrogen bond is formed within the molecule itself. So it cannot form another hydrogen bond with other molecule. Means it cannot form any intermolecular hydrogen bond. And this is possible, or intramolecular hydrogen bonding occurs only when a 6 or 5 membered ring can be formed as a result of this kind of chelation. Means if the hydrogen bond formed between the hydrogen atom and the electronegative atom of the same molecule occurs only if a 6 or 5 membered ring can be formed as a result of this kind of chelation. We'll understand this when we discuss some examples. So the first example is orthonitrophenol. This is C6H4 OH NO2. In this carbon it is OH, and in this carbon it is NO2 as a side chain. So this is orthonitrophenol. You can see in this case the hydrogen of the phenolic group, that is OH group, is hydrogen bonded to the oxygen atom of the nitro group, NO2 group. So this dotted line represents a hydrogen bond. So in this case you can see the hydrogen bond is formed between hydrogen atom and the oxygen atom of the same molecule. That is why it is called as intramolecular hydrogen bonding. Now, as a result of this hydrogen bond, you can see this molecule has undergone cyclization, right? If this hydrogen bond is not present, the OH will be present here and this NO2 will be here, and there will be no connection between these two. But since the hydrogen bond is formed, the molecule has undergone cyclization. A ring is formed. And how many members are present in this particular ring? 1, 2, 3, 4, 5, 6. So a 6-membered ring is formed as a result of this intramolecular hydrogen bonding in orthonitrophenol. Another example is orthonitrobenzoic acid. This is in this carbon you have a COOH group, and in this carbon you have a NO2 group, and a bond is formed between the hydrogen atom of this COOH group and the oxygen atom of the nitro group. So this is the hydrogen bond in orthonitrobenzoic acid, and this formation of hydrogen bond here also resulted in cyclization of the molecule, and it contains how many atoms? 1, 2, 3, 4, 5, 6, 7 atoms. So here a 7-membered ring is formed as a result of cyclization. Another example is salicylic acid. Salicylic acid, the structure is COOH here and OH on the second carbon atom. So in this case also, you can see a hydrogen bond is formed between the hydrogen atom of this COH group and the oxygen atom of this OH group. So this also results in cyclization. Another example is salicylic acid, salicylic aldehyde, that is OH group on the first carbon atom and CHO group on the second carbon atom. Here the hydrogen bond is formed between the oxygen of the aldehyde group and hydrogen of the OH group. This, as you can see, results in again cyclization. How many members are present in this new ring? 1, 2, 3, 4, 5, 6. So here a 6-membered ring is formed as a result of hydrogen bonding. Again, another example is orthochlorophenol. This is OH group and this is chlorine. And you can see a hydrogen bond is formed between this fluorine and this hydrogen. This results in a formation of 1, 2, 3, 4, a 5-membered ring is formed. So these are molecules or examples of molecules which can form intramolecular hydrogen bonds. Now consider the different isomers of orthonitrophenol. This is an OH group, this is a nitro group, and this is nitrophenol. There are 3 different isomers of nitrophenol. This is the ortho isomer, this is a meta isomer, this is a para isomer. This carbon that is attached to OH group is marked as position 1. Carbon attached to nitro group is marked as 2 here. So this is 2-nitrophenol. If this is the first carbon, this is the second one and this is the third one. So in this particular isomer, the nitro group is attached to the third carbon atom. So the name of this compound is 3-nitrophenol. Whereas in this one, this is the first carbon, second carbon, third carbon, and this is the fourth carbon. And nitro group is attached to the fourth position or fourth carbon atom. So it is called 4-nitrophenol. So orthonitrophenol is also called by the name 2-nitrophenol. Metanitrophenol is also called by the name 3-nitrophenol. And paranitrophenol is known by the name 4-nitrophenol. And these are the 3 different isomers of nitrophenol. Now the question is chelation formed in all these isomers? Means, is intramolecular hydrogen bonding possible in all these 3 isomers? The answer is no. Only orthoisomers can form chelation, or only orthoisomers can form in intramolecular hydrogen bonding. Meta and para isomers cannot form intramolecular hydrogen bonds. What is the reason? This is because in meta and para isomers, the electronegative atom and the hydrogen atom are at maximum distance apart, and therefore they cannot form intramolecular hydrogen bonds. But in the case of orthoisomers, the position of this electronegative oxygen and the electropositive hydrogen is favorable. They are lying close to each other. So the attraction between hydrogen and oxygen, the positively charged hydrogen and negatively charged oxygen is possible. Therefore, chelation occurs, or the intramolecular hydrogen bonding occurs only in orthoisomers. Meta and para isomers, the OH atom, OH side group and NO2 side group are farther away from each other. They are at maximum distance apart in the case of paranitrophenol, and therefore the electrostatic force of attraction cannot form. So it cannot form intramolecular hydrogen bonding. But this meta and para isomer can form intermolecular hydrogen bonding. That is, if another paranitrophenol comes closer to it, this oxygen atom can form hydrogen bond with the second paranitrophenol molecule. So it can form intermolecular hydrogen bonds. Both meta and para isomers can form intermolecular hydrogen bonds. What about ortho? Orthonitrophenol cannot form intermolecular hydrogen bond. It can only form what? Intramolecular hydrogen bond. Because once the hydrogen bond is formed inside the molecule itself, it cannot form another bond or another hydrogen bond with another molecule. So chelation is possible only in orthoisomers. Or in short, you can say intramolecular hydrogen bonding is found only in orthoisomers. Meta and para isomers can form only intermolecular hydrogen bonds. Now these two figures represent the intramolecular hydrogen bonding in orthonitrophenol and the intermolecular hydrogen bonding in paranitrophenol. In this orthonitrophenol, the OH group or the hydrogen atom of the OH group is bonded to the oxygen atom of the nitro group. So in this case, the hydrogen bond is formed within the molecule. That is called intramolecular hydrogen bonding. Now if another orthonitrophenol molecule comes closer to this, there will be no interaction between the first orthonitrophenol and the second orthonitrophenol. Why? Because the hydrogen bond is formed within the molecule itself. This oxygen and hydrogen is already bonded to each other. Therefore, it cannot form a hydrogen bond with another molecule. So, orthonitrophenol can form only intramolecular hydrogen bonding. But if you look at paranitrophenol cannot form intramolecular hydrogen bonding because the nitro group and OH group are lying far apart from each other. But it can form what? Intermolecular hydrogen bonding. This is one of paranitrophenol. This is second paranitrophenol molecule, and as you can see, a hydrogen bond is formed between the oxygen atom of the nitro group of the first molecule and the hydrogen atom of the second molecule. So in this way, a number of paranitrophenol molecules can associate to form a long chain. So let's compare the boiling point of these two molecules. Will they have same boiling point or will they have different boiling point? Of course, it will have different boiling point because in paranitrophenol, as we have already seen, it will form a large number of molecules will associate together by intermolecular hydrogen bonding. So what happens with molecular weight? Molecular weight will increase and therefore boiling point will also increase. So para derivatives undergo association, or you can say intermolecular hydrogen bonding, and this results in an increased molecular mass and therefore increased boiling point. So which will have higher boiling point? Paranitrophenol will have higher boiling point than orthonitrophenol because orthonitrophenol cannot associate like this. Orthonitrophenol will have low boiling point, or you can say they are more volatile than paranitrophenol. Means they will be easily evaporated or they will easily be converted to a gaseous state. So orthonitrophenols are more volatile than paranitrophenol. Or you can say intramolecular hydrogen bonding decreases the boiling point of a compound. Orthonitrophenol has low boiling point because of the presence of intramolecular hydrogen bonding. So you can say intramolecular hydrogen bonding decreases the boiling point of a compound. Or you can say the ortho derivatives are more volatile than para derivatives. So this is very important. Many questions can be asked from this. The question can be like this. Orthonitrophenol is more volatile than paranitrophenol. Why? Or which of these isomers of nitrophenol is more volatile? Or which of these have higher boiling point? Or explain that intramolecular hydrogen bonding decreases the boiling point of a compound. Explain with an example. So these are some questions that can be asked. Now, if you're given these two compounds, that is orthonitrophenol or a mixture of orthonitrophenol and paranitrophenol, can you suggest any one method by which you can separate these two molecules? Of course, based on this boiling point, you can separate these two molecules. You can simply steam distill the mixture so that the two different isomers can be separated. So if you steam distill the mixture, which compound will be coming out first? The compound with lower boiling point will come out first. And in this case, orthonitrophenol is having lower boiling point than paranitrophenol. So orthonitrophenol will distill out first, and what remains is paranitrophenol. So in this way you can separate a mixture of orthonitrophenol and paranitrophenol. Now let's check the solubility of these two isomers in water. Orthonitrophenol and paranitrophenol, which will be more soluble in water. Orthonitrophenol, we have already seen that it has intramolecular hydrogen bonding. So since the the oxygen and hydrogen is already bonded to each other, it cannot form hydrogen bonds with other molecules. So if you dissolve this orthonitrophenol in water, orthonitrophenol cannot form hydrogen bonds with water. Therefore, the interaction between orthonitrophenol and the solvent water molecule will be less. Therefore, its solubility will be less. Whereas, if you dissolve paranitrophenol in water, since paranitrophenol can form intermolecular hydrogen bonds with water like this, that is, the bond between a bond is formed between the oxygen atom of paranitrophenol and the hydrogen atom of water. So since this kind of bond can be formed, that is intermolecular hydrogen bonds can be formed between paranitrophenol and the solvent water molecule, paranitrophenol will be more soluble in water. So out of these two isomers, which will be more soluble in water? Paranitrophenol will be more soluble in water. Or we can say intramolecular hydrogen bonding decreases the solubility of a compound in water. So now we have seen two effects of intramolecular hydrogen bonding. First is that intramolecular hydrogen bonding decreases the boiling point of a compound. Also, intramolecular hydrogen bonding decreases the solubility of a compound in water. So which is less soluble? Orthonitrophenol is less soluble in water. So this is another question which can be asked. We will be given two isomers and you will be asked to identify the molecule with higher boiling point or lesser boiling point, or higher solubility and lesser solubility, and so on. It need not be orthonitrophenol, it can be any other molecule which shows hydrogen bonding, like salicylic acid or salicylic aldehyde, etc. So we will summarize what we have just studied until now. The first thing is that orthoderivatives are more volatile than paraderivatives. Secondly, orthoderivatives forms only intramolecular hydrogen bond. It cannot form intermolecular hydrogen bonds. Meta and paraderivatives forms only intermolecular hydrogen bond. It cannot form intramolecular hydrogen bonds. Then intramolecular hydrogen bond decreases the solubility of a compound in water. Intramolecular hydrogen bond also decreases the boiling point of a compound. So this slide is very important. Please bear in mind. Now let's study about the consequences of hydrogen bond. Consequences means the effects of hydrogen bond. As we have already understood from what we have studied so far, the molecules involved in inter and intramolecular hydrogen bond do not lose their identity. Why? Because hydrogen bonds are very weak in nature and that can be easily ruptured. But it will certainly affect the physical properties of substances. Means the presence or absence of hydrogen bonds in a molecule do not affect its chemical identity, but its physical properties may change. As we have already seen, the solubility, boiling point, etc. will change. So these are the different consequences of presence of hydrogen bonds. Hydrogen bonds will affect the melting and boiling point of a compound. It will result in association of molecules. It will affect solubility. It will affect viscosity, surface tension. Also, it will affect the boiling point. It will also affect we'll see how it will affect ortho and parametrophenols. So first, let's see the effect of hydrogen bond on melting and boiling point of a compound. If a molecule is bonded through intermolecular hydrogen bonds, it will form long chains, or it will associate to form long chains, and such molecules will be having higher melting and boiling point, because we need to supply more energy to break these hydrogen bonds, and therefore its melting and boiling point will be higher. Now let's compare the boiling point of hydrides of elements of group 5, group 6 and group 7. Group 5 means the nitrogen family, group 6 is the oxygen family, and group 7 is the halogen family. So if you plot the boiling point of the hydrides of these elements against its molecular weight, we will get a graph. So this is a graph which represents the hydrides of elements of group 5. Hydride of group 5 represents nitrogen family, that is nitrogen, phosphorus, arsenic and antimony. Hydrides of these elements means NH3, PH3, arsenic hydride and antimony hydride. So these are the hydrides of group 5 element, and you can see as the molecular weight decreases, that means as we move from right to left, the boiling point of these molecules is decreasing. But you can see there is a sudden increase in the case of ammonia. That is as we move from left to right, that is as we move from antimony hydride, arsenic hydride and phosphorus hydride, the boiling point decreases. But when we move from phosphorus hydride to nitrogen, ammonia, there will be a sudden increase in its boiling point. Now let's consider the let's see the graph of hydrides of group 6. Group 6 is the oxygen family, that is water, hydrogen sulfide, hydrogen selenide and hydrogen telluride. Again, as we move from right to left, that means as we move from hydrogen telluride to hydrogen sulfide, you can see the boiling point decreases. But there is a sudden increase in the case of water. Similarly, the same trend is shown by the group 7 elements, that is HF, HCl, HBr and HI. The boiling point decreases up to HCl, but there is a sudden increase in the case of HF. So in short, in all these examples, that is hydrides of elements of group 5, 6 and 7, the boiling point decreases with decrease in molecular mass. But the boiling point of ammonia, water and HF has larger values. What is the reason? That is because of the presence of intermolecular hydrogen bonds. We have already seen that HF, H2O and ammonia can form intermolecular hydrogen bonding, and because of the presence of these intermolecular hydrogen bonding, this molecule will associate to form a chain-like structure, and therefore we will have to supply more energy to break these bonds and to convert the molecule to gaseous state, or convert the substance into gaseous state. So therefore these molecules will have higher boiling point. Now if you look at water and hydrogen sulfide, you can see at room temperature water is a liquid, whereas hydrogen sulfide will remain as a gas. This is again due to the presence of intermolecular hydrogen bonding in water. We have to supply more energy to convert water from its liquid state to its gaseous state because of the presence of extrinsic hydrogen bonding. More energy is required to break these hydrogen bonds. Only then it can be converted into its gaseous state. So water at room temperature is a liquid, whereas hydrogen sulfide at room temperature is a gas. Similar is the case of HF and HCl. Hydrogen fluoride is a liquid at room temperature, whereas all other hydrides, that is HCl, HBr and HI, are gases at room temperature. Similar is the case of ammonia. Ammonia is also a liquid at room temperature, whereas the others are gases. So water, ammonia and HF are all liquids at ordinary temperature, while all other hydrates are gases. This is again due to the presence of intermolecular hydrogen bonding. The second consequence of hydrogen bond, or the second effect of hydrogen bond, is that it will lead to association of molecules. That is, two or more molecules of a compound can associate to form bigger molecules. Say for example, acetic acid. It is a carboxylic acid. The formula is CH3COOH. Now this molecule do not exist as a monomer, but it will exist as a dimer. This is one CH3COOH molecule. This is another CH3COOH. So this is one acetic acid molecule. This is another acetic acid molecule. So two acetic acid molecules will be hydrogen bonded with each other. You can see the hydrogen bond formed between the oxygen atom of the first carboxylic acid group and hydrogen atom of the second molecule. Similarly, a hydrogen bond is formed between the hydrogen atom of the first molecule and the oxygen atom of the second molecule. So in this way, acetic acid exists as a dimer because of the presence of association. What kind of hydrogen bond is it? Is it intramolecular bond or an intermolecular hydrogen bond? It is intermolecular hydrogen bond. Two different molecules are bonded to each other through hydrogen bond. So this is intermolecular hydrogen bond. Another example is alcohols. There is extensive association in alcohols. Say for example, this is an alcohol CH3CH2OH, ethanol, right? This is one ethanol molecule, this is another ethanol molecule. You can see a hydrogen bond formed between the hydrogen atom of the first ethanol molecule and the oxygen atom of the second ethanol molecule, right? Now this hydrogen can also associate with another oxygen atom of another alcohol. So in this way, a number of alcohol molecules can associate together. So this figure shows the extensive hydrogen bonding in alcohols. R represents the alkyl group. In this particular case, it is CH3CH2 group. So ROH is an alcohol. This is another alcohol molecule ROH. A third alcohol molecule ROH. So you can see a number of hydrogen bonds between these atoms. That is oxygen of the first alcohol and hydrogen of the second alcohol. Here also oxygen of the first alcohol with hydrogen of the second alcohol. So in this manner, a number of alcohol molecules can associate together. Now another effect of hydrogen bonding is the solubility. Means hydrogen bonding will affect the solubility of compounds. A compound will be more soluble in a solvent with which it can form hydrogen bonds. We have already seen how hydrogen bond affects the solubility of orthonitrophenol and pyronitrophenol. Now let's consider alcohol as an example. Alcohols are more soluble in water because they can form hydrogen bonds with water molecules. We have seen that in the earlier slide. Say this is ethanol, that is CH3CH2OH. This is ethanol. Now ethanol can form hydrogen bonds with water. This is intermolecular hydrogen bonding. Therefore, since they can interact with each other more strongly, ethanol will be more soluble in water. This is another figure which represents the same hydrogen bond. Instead of ethanol, I have shown it as a general example is given. Our R represents the alkyl group, ROH is the alcohol, and H2O, this is water. So hydrogen bonds formed between the hydrogen atom of alcohol and oxygen atom of water is shown here. So a compound will be more soluble in a solvent with which it can form hydrogen bonds, and lower alcohols like methanol, ethanol, etc. are soluble in water because they can form hydrogen bonds with water molecule. But if you consider organic molecules like alkenes, etc., they will be insoluble in water because there is no atom which can form hydrogen bonds with water. So in those cases, that is in the case of alkenes, etc., those molecules are insoluble in water. Now we have also seen that orthoisomers are less soluble in water than corresponding para-isomers. Another effect of hydrogen bonding is on the viscosity and also surface tension of compounds. Compounds which can form strong hydrogen bonds usually have higher values of viscosity and surface tension. Due to strong hydrogen bonding, water is more viscous than most of organic liquids. Other examples are concentrated sulfuric acid, glycerol, glycol, or honey, etc. All these are highly viscous due to extensive hydrogen bonding present in them. These are more viscous than even ethanol and methanol, etc. Simple alcohols. So these compounds have more number of hydrogen bonds formed, or they can form more number of hydrogen bonds, and therefore they are more viscous than simple alcohols like ethanol, methanol, etc. Because they have more number of OH groups, and since there are more number of OH groups, they can form more number of hydrogen bonds, right? So these compounds are highly viscous than simple alcohols. We know that the hydrogen bonding in hydrogen fluoride is much stronger than the hydrogen bonding in water because fluorine is more electronegative than oxygen. So we expect that the boiling point of hydrogen fluoride will be greater than the boiling point of water. But it is not actually found to be so. The boiling point of water is actually greater than the boiling point of hydrogen fluoride. And the boiling point of hydrogen fluoride is greater than the boiling point of water. So how can we explain this anomaly? How can we explain this variation in boiling point? Why is the boiling point of water greater than the boiling point of hydrogen fluoride, even though fluorine is more electronegative than oxygen? This is because in hydrogen fluoride, each molecule is hydrogen bonded to two other atoms, whereas in water, each molecule can be hydrogen bonded to four other molecules. So the total strength of these four hydrogen bonds in water molecule exceeds the total strength of two hydrogen bonds in HF. Okay, so since the number of hydrogen bonds formed in water is greater than the number of hydrogen bonds in hydrogen fluoride, the boiling point of water will be greater than the boiling point of hydrogen fluoride. So though HF forms stronger hydrogen bonds than water, the total strength of the four hydrogen bonds in water is greater than the two hydrogen bonds in HF molecule. That is why water is having higher boiling point than hydrogen fluoride. And if you consider the number of hydrogen bonds in NH3, each NH3 molecule forms hydrogen bonds with only two other molecules. So the boiling point of ammonia will be less. So the strength of hydrogen bonding is greater in water than HF, which is greater than in ammonia. Therefore, the boiling point of these molecules are in the order water, hydrogen fluoride, ammonia. Because of this, water is a liquid while ammonia is a gas at room temperature. So this is another question which is often asked. Now another question is, orthonitrophenol is more volatile than paranitrophenol. Why? Actually, we have seen the answer to this earlier itself. In the case of orthonitrophenol, there is intramolecular hydrogen bonding. It cannot form intermolecular hydrogen bonding with other orthonitrophenol molecules. Whereas in the case of paranitrophenol, it can form intermolecular hydrogen bonding, and a large number of paranitrophenol molecules can associate together to form long chains. Therefore, paranitrophenol have higher boiling point than orthonitrophenol, or we can say orthonitrophenol is more volatile than paranitrophenol. Another question is, orthonitrophenol is less soluble in water than paranitrophenol. Why? We have already seen this. This is again because of the type of hydrogen bonds formed. Orthonitrophenol cannot form intermolecular hydrogen bonding with water, whereas paranitrophenol can form intermolecular hydrogen bonding with water, means they will interact strongly with water and therefore they will be more soluble.